Welcome to this deep dive, tailored just for you and brought to you in partnership with Scholar Academy. We're digging into the really fascinating world of robotic mapping and localization today.
That's right. We're looking at a system called Maplab 2.0.
Yeah, Maplab 2.0. And we're basing this on, well, excerpts from a pretty detailed research paper that introduces it.
hmm A comprehensive one. It really lays out what Maplab 2.0 can do.
So our mission here is to, pull out the key stuff. What makes this Maplab 2.0 such a big step forward in SLAM, that's Simultaneous Localization and Mapping,
Right.
and why does it matter, for robotics, for the future, and, well, for the kind of innovation we encourage at Scholar Academy. So maybe let's start there. What is SLAM exactly? Why should we care?
Okay, so SLAM, at its heart, it's how a robot can build a map of a place it's never seen before.
While it's moving around.
Exactly.
Yeah.
While it's moving around and figuring out where it is on that map it's building. Think like a robot vacuum. It doesn't start with a map of your room, right? It learns the layout as it cleans, and it knows, okay, I'm near the couch now.
Yeah.
That's fundamental for, well, any robot that needs to operate on its own.
Got it. And where is this tech making a difference? Like real-world examples.
Oh, loads of places.
Yeah.
Autonomous driving is a huge one.
Yeah.
Cars need to know exactly where they are relative to, lanes, people, other cars.
Mm,
And the map is always changing.
right.
Or think about warehouse robots. Picking and packing things. They need SLAM
Yeah.
to navigate those big spaces and grab the right item precisely.
Okay.
Even augmented reality. When you see digital stuff overlaid on your phone screen,
Yeah.
SLAM is what locks those virtual objects to real points in your room.
Huh. So it really is that foundational piece for robots doing things in the real world. Now, the paper mentions challenges with long-term mapping. What's the difficulty there? Mapping over time or big areas?
Well, the problem is errors. Tiny errors in estimating movement or seeing features, they add up over time and distance.
Like drifting off course.
Exactly. You think you're going straight, but tiny miscalculations mean you end up way off. And then you also often need to combine maps, maybe from different robots, or from the same robot mapping at different times. Getting those to fit together correctly, that's tricky.
I see. Like trying to stitch together different surveys of a big area. They might not quite match up perfectly. Okay, so SLAM has evolved. The paper talks about multimodality being really important now. What's that?
Right, so early SLAM often used just one sensor, maybe a camera. Multimodality just means using multiple different types of sensors together, fusing the data.
Like what kinds of sensors?
Well, cameras, obviously, but also LiDAR. That's the laser-based depth sensor.
Hmm.
GPS for outdoor location. Wheel encoders, tracking how far the wheels have turned.
Yeah.
Even semantic information, understanding what objects are in the scene.
Why the push for using all these different senses? What's the big advantage?
Robustness, mainly. Real world is messy, right? Lighting changes, things get blocked. If one sensor struggles, maybe the camera can't see in the dark. Others, like LiDAR or an IMU, can fill in the gaps.
Oh, okay. So it makes the whole system more reliable.
Definitely. And it also means different kinds of robots can work together. Maybe one robot has great cameras, another has precise LiDAR. They can pool their data.
Makes sense. Now, the paper mentions other open source SLAM systems like OrbiSLAM 3, RTAP Map. What are their limitations? What's Maplab 2.0 trying to fix?
Yeah, those are great systems, don't get me wrong. But they often tie everything really tightly to specific sensor setups.
Meaning it's hard to change them?
Exactly. If you want to add a new sensor type or maybe try a whole new way of processing data, you might have to rewrite huge chunks of the code. The different parts like motion estimation, localization, finding features, they're all kind of tangled together,
Okay.
which is a big headache for researchers. It slows down trying out new ideas, especially with all the cool deep learning stuff coming out for perception.
So modifying them is like major surgery. Where does Maplab 2.0 come in then?
It's built differently, much more flexible, more modular. The idea is you can plug in different sensors and processing modules more easily, like Lego bricks, kind of.
Okay, Lego bricks for SLAM. I like that. So Maplab 2.0 is this adaptable platform. The paper says multi-session, multi-robot, and versatile multimodal mapping. Let's break that down. What new sensors does it handle?
So the original Maplab was mostly visual-inertial cameras and IMUs. Maplab 2.0 adds native support for LiDAR, GPS, wheel encoders, even, like we said, semantic object data.
Wow, quite a list.
And crucially, it's designed so adding more sensor types later shouldn't be a massive undertaking.
And it's not just the sensors, right? It mentioned integrating external components. What does that mean?
Right. It has these specific interfaces like connection points where you can plug in your own custom code, maybe a new way to find visual features using deep learning, or a different method for loop closure.
Loop closure that's recognizing places you've been before.
Yeah, exactly.
Hmm.
Crucial for fixing those accumulated errors we talked about.
Yeah.
So this plug-and-play thing makes it great for research. You can test new deep learning modules quickly, which often get developed separately.
Sounds like it could really speed things up for researchers. Okay, what about online collaborative SLAM? That sounds futuristic.
It's pretty cool, yeah.
Yeah.
It means multiple robots can build one shared map together in real time.
Wow.
It uses something called submapping. Each robot makes its own little local map, a submap. Then it sends that submap to a central server.
Okay.
The server takes these submaps from all the robots, cleans them up a bit, optimizes them, and figures out how they all fit together into one big, globally consistent map. It can even send updates from this big map back to the robots.
So they all benefit from each other's discoveries, like a hive mind for mapping.
Kind of, yeah. It gives them a much better overall picture of the environment.
Okay, that's powerful. So let's nail down the main contributions the paper emphasizes for Maplab 2.0.
All right, they list three key things. First, it's this open source framework that handles way more sensor types and combinations than pretty much anything else out there.
Okay, unparalleled versatility.
Second, this online collaborative system, using the submaps in the server to build these big, consistent, detailed maps for multiple robots.
Got it.
And third, the flexibility. You can plug in basically any number of custom features, descriptors, loop closures. They show examples using 3D LiDAR points and even recognizing objects for loop closure.
Right, a platform that really enables new research and development,
Yeah.
very much in the spirit of what Scholar Academy promotes. Okay, let's get into the nuts and bolts. The architecture. 3 main parts.
Yep, 3 main components working together. The mapping node, the mapping server, and the offline console.
Let's start with the mapping node. What does that do?
The mapping node runs on each robot. It takes the incoming sensor data camera images, LiDAR scans, IMU readings, whatever, and builds what's called a multi-modal factor graph.
Factor graph. Sounds technical.
It is a bit, but think of it like a network. Nodes in the network are the robot's state, its pose, velocity, things like that at different times, plus the locations of landmarks it sees. The connections, the edges, represent constraints from the sensor data.
So it's like a mathematical map of relationships.
Pretty much. And a key thing is, this node isn't tied to one specific way of estimating motion, unlike the original Maplab. It can use different odometry sources, use IMU data if it's there. It handles different 3D landmarks, different constraints, and it even stores the raw sensor data. They call it resources if you need to look at it later.
Okay, so each robot builds its own local piece of the puzzle using the mapping node. What's the mapping server for then? This is the new part.
Exactly. The mapping server is what enables that online collaboration. It's the central hub. It receives those submaps from the different mapping nodes on the robots.
And does what with them?
First, it pre-processes each submap. Now, optimizes it locally, checks feature quality, looks for loop closures just within that small map piece. Then it stitches together submaps on the same robot. And critically, it works on the global picture, finding connections or loop closures between maps from different robots. That's how it builds and optimizes the big, shared, multi-robot map.
So it's the master coordinator putting everything together.
Right. And an interesting detail is that it shares a lot of code with the offline console, which makes adding new features easier down the line.
Okay, and that brings us to the third piece, the offline console. What's its job?
The offline console is basically the toolbox for doing more heavy-duty processing after the mapping is done, or for working with data you already collected. It builds on the tools from the original Maplab, but updated for all the new multimodal stuff.
What kind of tools?
Things like batch optimization, refining the entire map at once for maximum accuracy, merging maps from different sessions, getting rid of bad data points, outlier rejection, simplifying the map by picking keyframes or sparsifying it. And it now has specific tools for LiDAR loop closure, like ICP.
ICP.
Iterative closest point. It's a common way to align 3D point clouds. The console also manages those raw data resources and lets you export the map. Plus, it's extensible with offline plugins. That's how they added things like the LiDAR registration and the semantic loop closure we'll talk about.
Okay, so node on the robot, server for collaboration, console for deep analysis and refinement. Got it. Now, inside these maps, what are they actually made of? You mentioned missions and factor graphs.
Right. So a map in Maplab 2.0 is basically a collection of missions. Each mission is just one continuous mapping session.
Like one robot's trip.
Yeah, or one data collection run. And underneath, holding it all together, is that factor graph structure we mentioned. The vertices are states, robot poses, velocities, IMU biases, landmark positions. The edges are the constraints, the information linking them.
What kinds of constraints? What do the edges represent?
Several types. You have IMU edges linking poses over time based on inertial data. Relative pose constraints, which come from odometry, how the robot thinks it moved, or from loop closures. Landmark observation edges, linking a landmark to the robot poses that saw it. And absolute constraints, like from GPS or known markers, pinning down a pose in the global frame.
And it handles uncertainty.
Yes, very carefully. It uses covariance matrices to represent how certain or uncertain each measurement is. And for loop closures, it uses something called switchable constraints.
Switchable.
Yeah, it means the optimization process can effectively ignore a loop closure if it seems really inconsistent with everything else. It makes the system much more robust to bad loop closures, which can definitely happen.
Okay. And how does it find those landmarks in the first place, the visual ones?
It uses standard techniques, detects features in images. It supports things like ORB, brisk, freak features. Then it tracks them across images as the robot moves, matching descriptors.
Descriptors being like fingerprints for the features.
Exactly. And once a feature is seen from enough different viewpoints, its 3D position can be calculated, triangulated, and boom, you have a visual landmark in the map.
And recognizing places it's seen before.
Yeah.
Loop closure.
For visual loop closure, it looks at features in the current view and tries to match them to the 3D landmarks already in the map. It often uses covisibility, basically, only checking against landmarks likely to be visible from the current spot.
Makes sense.
If it finds enough good 2D to 3D matches, it uses algorithms like P3P inside Ransack. That's a robust estimation method to figure out the transformation. If it's confident, that transformation becomes a loop closure constraint added to the factor graph.
Pulling the map together.
Right. They also mention an alternative way. By merging landmarks, it decides they're the same, and minimizing the reprojection error, which avoids needing to define the loop closure uncertainty explicitly.
It sounds like it's really beefed up how it handles features. The paper says any number of different feature types. How does that work?
Yeah, that's a big deal. It means you can use different feature detectors simultaneously, maybe ORB features, and also some fancy new deep learning features. You can use a built-in tracker or plug in your own. And it supports different descriptor types. Binary ones like ORB, matched efficiently, and floating point ones, often from newer detectors, using FLAN for matching.
FLAN.
Fast library for approximate nearest neighbors. It's good for those floating point descriptors. And you can tune the parameters separately for each feature type.
Super flexible. What about non-visual landmarks? Things from LiDAR or depth cameras?
Right. It can handle those too.
Yeah.
So the sensor gives you a direct 3D point, like from an RGBD camera or LiDAR. In these cases, the 3D position isn't usually triangulated from 2D views. It might be averaged from direct 3D measurements.
And the error is different.
Yeah, instead of reprojection error in the image, the error term in the factor graph is usually based on the direct 3D distance, Euclidean distance, between the observation and the landmark's estimated position.
Yeah.
And loop closure with these becomes 3D to 3D matching, often using things like ICP within Ransack.
Okay, this paints a picture of a really adaptable system. Let's see it in action. The paper has use cases. First up, the HEL-TI 2021 dataset validation. What was that about?
Right, the HEL-TI dataset is tough. It's got data from indoor offices, outdoor construction sites, really diverse. They used 9 sequences from it, skipping some easier ones. Some sequences were even in the same place, so they could test how well it aligns maps from different runs.
This is localization.
Exactly, and the dataset has tons of sensors, 5 cameras, IMU, LiDAR, so a good test bed.
And how did Maplab 2.0 stack up against other methods?
They tested it with different odometry inputs, Rovio, OAKFI, AS, FastLIO2. They also added external features like Superpoint and SIFT, used all the features for loop closure, refined with ICP. The results. Measured by absolute position error, Maplab 2.0 significantly beat the vision-only systems like Orbislam 3 and original Maplab.
Better than the vision ones, okay.
And interestingly, it could even improve the results from FastLIO2, which is already a top-tier LiDAR inertial system.
Wow, so it can take good data and make it even better.
Seems so. They showed an example fusing Rovio odometry with SIFT features led to big accuracy gains pretty quickly. Right. Really shows the power of fusing different data types well.
That's impressive. Okay, next use case. Large-scale multi-robot, multi-session mapping. Sounds like a real-world torture test.
It was definitely ambitious. They used it in a big training facility, simulated urban streets, collapsed buildings, indoor-outdoor transitions. Really complex.
How much data?
They collected 23 separate runs with a handheld device, 5 cameras, LiDAR. Over 10 kilometers traveled, 2 hours of data total. Used OKVIS for the initial odometry on each run.
And how did they merge all those 23 runs into one big map?
They used the mapping server first for the online collaborative part, merging the first 5 runs. Then they used the offline console's multi-session tools to merge the other 18 runs into that map.
Okay.
They used visual loop closures between the different runs, plus RTK GPS data when they had it, to keep everything aligned globally. And they refined everything further using LiDAR registration, aligning point clouds both within runs and between different runs.
Did it work?
The paper shows the final map. And yeah, it looks like a really detailed, consistent map of this huge, complex area built from all those separate pieces. They also tested the server performance on a standard data set, Euro-C, and found it got similar accuracy to processing everything sequentially, but much faster.
Speed and scale, key for real applications. Okay, the next one sounds really novel. Visual tracking on projected LiDAR images. What on earth is that?
Yeah, it's clever. They basically took the 3D LiDAR point cloud
Yeah.
and projected it onto a 2D plane to create an image. But instead of colors, the pixel values represented range or intensity from the laser. They cleaned it up a bit using fusion and in-painting.
So a fake 2D indoor made from 3D data.
Pretty much.
Hey, but
And then they ran standard 2D visual feature detectors and trackers, superpoint and superglue on these LiDAR images.
why?
Well, because each pixel in this fake image comes from a 3D point, the features you detect automatically have depth information. This apparently helps initialize the 3D landmarks more easily and makes loop closure more robust than just using camera features alone.
Huh. So what's the benefit?
They showed on a Hill TI sequence that landmarks found this way map structural things more accurately than just visual points, thanks to that direct depth. But they also noted these LiDAR features can be a bit noisy sometimes, maybe due to moving objects or sensor noise.
Interesting trade-off. A really creative way to blend sensor types. Okay, last use case. Semantic-based mapping. Bringing in object understanding.
Exactly. This really shows the extensibility. They use Mask RCNN, a deep learning model, to detect objects like chairs, tables, walls in the camera images.
Okay.
Then they extracted a descriptor, like a fingerprint, for each object using NetVLAD, and tracked the objects over time using Deep Sort.
So it knows that's the same chair I saw a second ago.
Right, and these tracked semantic objects become landmarks in the map, but they have a label chair, table, etc.
And how does that help?
It allows for semantic loop closure. The system can say, hey, I see a chair here with this description, and I saw a chair way back there with a very similar description. Maybe it's the same place.
Using object identity for loop closure.
Precisely. After checking the geometry makes sense, it adds a loop closure constraint based on matching these semantic objects. They showed results on an indoor data set where adding these semantic constraints significantly reduced the drift in the map.
So the map becomes not just geometrically accurate, but semantically richer, too. Very cool. Okay, let's wrap this up. What's the big picture here for our listeners, maybe especially those connected with Scholar Academy?
Well, Maplab 2.0 is clearly a huge step. The flexibility it offers, bringing together all these different sensors in a collaborative way, it's unprecedented, really. The bottom line is, this kind of robust fusion makes robots much more capable in messy real-world places. That's key for autonomy.
Yeah, you see it in the results. Getting state-of-the-art accuracy, handling these large-scale multi-robot scenarios, even bringing in advanced stuff like semantics or using LiDAR in new ways. It's pushing the envelope for what autonomous systems can do.
And being open source is massive.
Yeah.
It lets the whole community build on it, contribute back.
Yeah.
That collaborative spirit, that's something we really value at Scholar Academy too. It accelerates everything.
So think about the impact. Robots that are more reliable in complex jobs, teams of robots working together better, robots that actually understand more about their surroundings, not just the geometry.
And if you want the nitty-gritty details, the paper and the code are out there. You can really dive in.
Definitely. So here's a final thought, particularly for our Scholar Academy listeners. Robots are becoming more and more part of our world, and their ability to see, map, and understand that world accurately is absolutely fundamental. Maplab 2.0 is a fantastic example of progress here. It hints at a future where autonomous systems are way more reliable, adaptable, and maybe even intelligent.
Hmm.
So the question to ponder is, what totally new things become possible when robots can perceive and map their world this well? What applications haven't we even thought of yet? Something to chew on after this deep dive.